Oh, yeah, here we go. Thank you. So my name's Adrian Hopgood. I'm Professor of Intelligent Systems. So unlike most of the speakers today, I don't have a medical background. I'm specialised in artificial intelligence and all its practical applications. Clearly not a master of the technology, though. So what I'm going to cover today is a brief introduction to artificial intelligence and potential applications in healthcare, and then I'm going to talk specifically about some work that we've done with Jim Kahn's group about predicting patient outcomes following surgery. But let's start with that introduction to AI. What is AI? Well, a standard definition is mimicking human mental faculties with a machine. This is a long-standing definition that can more or less be traced back to Alan Turing's paper in 1950, but it's quite broad, and I think that's why there are so many different interpretations. First of all, it defines the challenge of AI, but not the techniques. And there are a whole stack of other questions that it raises. Does the AI need to work like a human, or are you just interested in the outcomes? And so forth. I won't go into all of those. The other thing is that our understanding of what AI means is constantly changing. So here's a quote from Rodney Brooks, one of the famous AI pioneers, who says, every time we figure out a piece of it, that is to say a bit of AI, it stops being magical and we say, oh, that's just a computation. So back when I first started working in AI in the 1980s, a big challenge was building a chess player. Well, that was solved very effectively in 1996 when Deep Blue beat the Grandmaster. Similarly, character recognition, specifically handwriting, and speech recognition and so forth. These are tasks that are essentially solved, and it's AI out there in the real world, and we kind of no longer think of it as AI. Turning now to the tools, I said that the tools are sort of not laid down in that definition of AI. They can broadly be broken down into two families. There's a long tradition of knowledge-based AI, which is where you capture human expertise in a computer system in a way that's designed to be flexible so it can evolve and it can learn and you can add new knowledge. On the other side of my Venn diagram, we've got computational intelligence, which is data-based. And this is where there's a big focus at the moment. So machine learning, neural networks are effectively the main tool of machine learning. Deep learning are just big neural networks. And what you're doing there is you've got a system that learns from hundreds or thousands of examples, but by and large, these machine learning systems are just classifiers, given lots of examples of type A, type B, type C, and then present it with something new, and they'll say, oh yeah, I know that, it's a type A. Essentially, they're just classifiers, really useful, but I think to build truly intelligent AI systems, you do need that knowledge-based component. The two approaches are complementary, they're not exclusive. And this is probably the moment to plug my book, Practical Guide to Artificial Intelligence, in its 4th edition, which covers all of these kind of techniques, should you be interested. In terms of applications in the medical domain, according to Schmidt, there are 4 top areas where there's most activity at the moment. Diagnosis, drugs development, treatment personalization, and improved gene editing. And I'm just going to focus now on the work we've done on predicting patient outcomes, one of the aspects of treatment personalization. So I won't go through all the stats about colorectal cancer, you'll know those, but one of the key points is that the cost of hospital care is a significant part of the cost of the treatment. So predicting patient outcomes can be a big help in managing that stay in hospital. So we're looking at 3 potential measures that we can predict: length of stay, readmission, and mortality. So Jim's team, we've worked together on using their database of some 4,000 plus anonymized patient records, each patient record with 47 variables. Some of those are input variables describing the characteristics of the patient and their operation. Some of them are output variables describing what's happened to them post-surgery, such as mortality, readmission, length of stay, etc. what we did is two phases. First of all, we looked at the data and looked for patterns within the data. So this is our data analytics phase, looking for which variables really matter. So in the case of length of stay, we can see here briefly that essentially a red bar means a long length of stay, a green means a short length of stay. So it's good to have elective rather than emergency surgery. It's good to be young, it's good to be fit, it's good to not have complications, it's good to have robotic surgery, it's good to have a low BMI, possibly, but actually that's a bit less clear-cut, and I'll come back to that BMI one. And it's good to have laparoscopic surgery. So armed with that initial data analytics phase, we were then able to build our predictors. We built two versions, actually, one using all the input variables and one just using the variables that our data analytics had shown to be the most relevant. So here's a scatter plot of predicted variables versus actual values for the length of stay. And there's quite a wide scatter there, and the root mean squared error is quoted here. And that's because actually tying down the actual precise length of stay is quite hard. However, if we actually look at it differently and look at whether our predictor is accurate at predicting whether or not a patient stays in hospital for more than 6 days, then it becomes much more reliable. We may not get the precise figure, but we're 83% accurate in predicting whether or not they'll stay for 6 days or more. And the result is almost exactly the same, whether we use the full set of 27 input variables or the selected key 10 variables. So that's interesting in itself as well, because it does mean we could streamline the variables needed for these models. Looking now at readmission, same sort of process, starting with the data analytics phase, where green means not readmitted, so it's best to have had no previous surgery. It's best to have a shorter operation time. Again, it's better to be elective. Better not to have had a preoperative M stage. Better not to have had the additional procedures. Better to be fit, etc. Now, because readmission is a kind of yes-no classification, you can present the results in a different way using a so-called ROC curve, receiver operating characteristic, which is a way of presenting the accuracy, sensitivity, and specificity all in one curve. So the closer it is to the top left-hand corner, the better. And you can see that we're getting accuracy of 87.5%, sensitivity and specificity of a similar values as well. And that's using a type of neural network called a long short-term memory. Turning now to mortality. Again, the green bar is good, meaning a long mortality window beyond 2 years. And similar patterns emerge. Elective surgery is better than emergency. Good to have a low BMI. It's good to be aiming for a curative surgery rather than palliative. It's good to have no complications. It's good to be fit. And it's good to not have a preoperative M stage. And our predictor here, again using the bidirectional long short-term memory network, provides better accuracy again if we look at the 91 days mortality. So we're looking, again, by focusing here on the 91 days, that makes it a yes-no classification, so you can present it in this way with accuracy, sensitivity, and specificity all over 90%. And again, we had very similar results using this subset of data rather than the full data set. So why does this matter? A number of things. First of all, better patient risk stratification, better patient care plans, better prioritization of resources, better informed patient consultation and decision making. So what happens next? Well, we've published these results in Discover Oncology, came out just 3 or 4 months ago. And it's attracted a little bit of interest, as you can see from the university's webpage there. This has still nevertheless been a relatively small study. We'd like to pool data with other centres. We'd like to consider the possibility of looking at the photo and video evidence that goes alongside the surgery to get some more precise predictions. And one of the suggestions of the reviewers of the Discover Oncology paper was that maybe we should separate out the colon and rectal cancer groups. And actually we started to do that. So this is just a sneak peek, as it were, of some data that we're preparing. But we can see that the length of stay tends to be longer for the rectum patients versus the colon patients. And I mentioned earlier that the BMI was not a particularly strong indicator for length of stay. Well, it turns out it is a reasonable indicator for length of stay for the rectum patients, less so for the colon patients. But these are sort of results that we'll be analysing in the coming weeks and months. So I'd like to finish off with the acknowledgements that all the data analysis at the university has been done by my colleague, Dr. Shamsul Massam, and we're grateful to Jim and his team for providing the data and helping us to process and understand those data. Thank you very much.
Thank you.